In this video, we're going to talk about the activity series, which predicts whether or not a single replacement reaction will occur. So here we see a list of metals, ranking them in order of reactivity, where up at the top you have the most reactive metals, and down at the bottom you have the least reactive metals. And then you have a secondary list that incorporates just the halogens, and the most reactive halogens at the top, and the least reactive halogen at the bottom. So when we look at this list, you can see that the elements up at the top that are the most reactive are the metals that you would think would be the most reactive. They're the ones with low ionization energies. You have the alkali metals and the alkaline earth metals, and then down near the bottom you have the ones that are closer to almost being in the metalloid area of the periodic table that don't really get rid of their electrons very easily and have higher electronegativities. So they're less likely to form positive ions than these ones. So when they're competing for a reaction, these ones are more likely to lose their electrons than these ones, and that predicts whether or not a reaction will occur. So if we take a look over here, if I put aluminum metal in a solution of zinc chloride, you can see that aluminum is more reactive than zinc. Therefore, a reaction will occur. The aluminum will displace the zinc from the zinc chloride and give you aluminum chloride as a product, and then zinc by itself. One thing I want to point out is that you can see that while zinc is with 2 chlorides here, aluminum is with 3. So that is dependent on the charges of the ions combining. Zinc's a +2 ion, chloride's -1, so that's why that formula is what it is. Over here you can see aluminum is +3, so that's why it's with 3 chlorides. And then to worry about how many of each thing you have on both sides, as a second step after you establish the formulas, you balance using coefficients. However, if you see silver down here, if you put a piece of silver in a solution of zinc chloride, nothing's going to happen because silver is less reactive than zinc and therefore is less likely to want to be an ion and won't displace it. If you look down here, it shows the reactivity of the halogens. So this right here, metal replacing metal, is a cationic single replacement. Down here we're looking at anionic single replacement because nonmetals are the ones that form anions. We know that fluorine is the most reactive nonmetal and it's also the most reactive halogen as a result. And it's more likely to gain electrons than any of the other ones, which is why if you have it as a neutral element and you put it in the presence of salt containing a less reactive halogen, it will displace it. So you can see here fluorine will displace chlorine because it's more reactive, and then form magnesium fluoride and chlorine gas. However, if you try to do that with iodine, since that's less reactive, it won't displace the chloride ion. Now, in addition to just this ordering or ranking of the metals, you can see that there's also little descriptions written to the side, and that's what we're going to look at on the next slide. So, up at the top where the most reactive things are, you'll find that they react with cold water, they'll react with steam, they'll react with acids, they'll react with oxygen. They react with almost everything because they're super reactive. So, here's just showing potassium, which is an alkali metal, reacting with water. So what it will do is it will displace one of the hydrogens from the water to form potassium hydroxide and produce hydrogen gas. I just want to point this out because a very common mistake people make is they'll put K2O, trying to replace both hydrogens from the water. It only will displace one. Okay, so you end up with a hydroxide, and then you get hydrogen gas. And then to worry about the amount of each element on both sides, you balance it using coefficients. You can also see that if you took another one of these alkali metals and you react it with an acid, it will also displace hydrogen in that, so you end up with hydrogen gas as well. Aluminum is in the next category, so I picked that one. It won't react with cold water, however, it will react with steam. And in much the same way, it will displace one of the hydrogens to form a hydroxide. Again, aluminum hydroxide, aluminum's +3, hydroxide's -1, and that's why you get that formula, and it also results in the production of hydrogen gas. And it's also reactive enough to react with acids. You can see that anything above here is reactive enough to react with oxygen to form oxide. So if you took an alkali metal in the presence of oxygen, it's going to form an oxide, and the same deal with this. And that would also be true for these and these as well. Looking at this page, we're going to look at the less reactive metals. So you can see that I took nickel from this category. If you put that in liquid or gas water, it would not react. So liquid, water, or steam, no reaction. However, it is still reactive enough to displace hydrogen in a single replacement reaction with an acid in order to produce hydrogen gas. And you can see that that category is above hydrogen on that list, and that's why that's capable of occurring. Looking at the list below that, you can see that they're not really that reactive. They won't react with acids, they won't react with water or steam, but they will still react with oxygen to form oxides. And then if you look at anything in the bottom group, they're mostly unreactive. So almost anything's not going to react with gold. There's almost nothing that will react with gold. So that's our activity series.